So remember we have a test on Friday. Again, just like before, you can start the exam at 8 a.m. which will have to be done by 9:50. This will be the last section that's on the exam when we start today here. It's a continuation of what we did before break. So let's remind ourselves of a couple of definitions. So what does it mean for a set to be linearly independent? It's the other way around. So if it's linearly independent, yeah, it's one solution to what in particular? So linear independence and span both have to do with linear combinations, right? So what specific linear combination are we talking about if we're talking about linear independent? What specific linear combination are we talking about? Linear combination of which specific vector? The zero vector, right? So if I have a linear combination that gives us the zero vector, what has to be true? What has to be true about the constants? Each one of them is zero. Good. There's exactly one way to write the zero vector as a linear combination, and that is to use all zeros for our constants, right? What does it mean for a set to span a vector space? It has to do with linear combinations. What does it mean for a set to span a vector space? So if I know that none of these are linear combinations of the others, that's another way to say linear independent. Okay, but span has to do with linear combinations as well. So if I start with some vector in V, what can I do? What can I do with that vector? It has to do with linear combinations. What do you think it means? Say it again. He says if whenever the W vector. Yeah, the W vector is in V, then what can I do? So linear combination of which ones? Which vectors do? If I want to say that this specific set spans V, what linear combination do you think I want? Yeah, I probably want to do a linear combination of the V's, right? So there exists C1, C2, out to Cn, such that C1, V1 plus C2, V2 out to Cn, Vn equals the W. Span means that I can write every vector in V as a linear combination of the V's. That's what spanning means, right? There's a set of vectors that generates every vector in the space. But again, remember our idea of that is the IJK that you use in Calc 3, right? I can write every single vector as something times I plus something times J plus something times K. The IJK would span R3. That's what that means, okay? Linear independent, again, means there's only one way to write the zero vector, and what that gives us is uniqueness for the representation. So let's look at some of these examples to start with. How do we check whether sets are linearly independent or span? What do we do? For either question, what do we do? Make a matrix and do what with the matrix? Once you make your matrix, what do you do with it? Row reduce it. For linear independence, what are you looking for? Pivots in every column. For span, you're looking for pivots in every row, right? Okay, so let's do this one. It's the same concept either way, right? The first thing you're going to do is check whether it's linearly independent or span. So you're going to make a matrix and row reduce. That's first step, right? How do we form the matrix? What do I do with the vectors? How do I write them as? Down the columns. Good. So I'll take my 1, 0, 0, 0, 1, 0, 0, 0, 1, write it down the columns, right? Do I need to do anything to row reduce it? No, it is row reduced, right? Why is this set then linearly independent? What are we looking at? There's a pivot in every single column, right? Why does it span? Pivot in every single row, right? That's why it was linearly independent and span. So just to write that down, linearly independent, the reduced row echelon form has a pivot in every column. Spans, the reduced row echelon form has a pivot in every row. That's what we're looking for those two conditions. Why do we look for those again? Remember, for linearly independent, the only linear combination that can give you the zero vector is to use all zeros. If you don't have a pivot in every column, that corresponds to a free variable, which means your homogeneous system has how many solutions if you have a free variable? Infinitely many. So there's not just one way to write the zero vector, there's infinitely many ways to write the zero vector, right? So it can't be linearly independent. That's why we need a pivot in every column. For span, we need a pivot in every row because that means that no matter what vector we put on the right-hand side, if we think about augmenting, I can always solve it, right? If I have a pivotless row, if I have a row of zeros, then I can find vectors to augment where I wouldn't be able to solve the system, so it doesn't span. Notice in this case, if I want both, it needs to be a square matrix, right? To start with. Okay, we're going to come back to that idea later. All right, what about the next one? Same idea, right? How do we make our columns of our matrix when we want to talk about polynomials? What do? You use the coefficients, right? So our first column here would be 1, 0, 0 for the constant, right? The next one, there's no constant, 1x and no x squareds. The next one, there's no constant, no x's, and 1x squared. That looks exactly the same, doesn't it? All right. Pardon me. So in both cases, we have a set that's linearly independent and span. What that means is that we can write every single polynomial. In this case, we could write every single polynomial as a constant plus x plus something times x plus something times x squared, every second degree or less polynomial, right? And since it's linearly independent, it's unique. There's only one way to do it. And you think about doing that every time, right? You do that as a plus bx plus cx squared gives you a unique polynomial, right? A unique second degree or less polynomial, I should say, right? Okay. So this gives us the idea of the definition for a basis. So if we take a subset of a vector space, then we say that S is a basis for V if, 1, S is linearly independent, and 2, the set spans. All right, so in this example, we're going to show that this set is a basis. We want to show that it's linearly independent and it spans. What do you think we're going to do? make a matrix and row reduce it. Good. What's the first column of your matrix going to be? Pardon me. First column of your matrix going to be? Yeah, 1, 0, 0, 0, right? Next column will be 1, 1, 0, 0. Next column will be, that should be a comma, not a period, by the way. Next column should be 1, 1, 1, 0, and the last one should be 1, 1, 1, 1, right? We're just picking off the coefficients, right? Now, you could type this in your calculator and row reduce, but if you look, just looking at it, what are you going to get for the reduced row echelon form? Yeah, we're going to get the identity matrix, aren't we? And isn't that what we need to see if it's going to be a basis? Don't we need to see the identity matrix when we row reduce? I need a pivot in every column and I need a pivot in every row. The only way to do that when I row reduce is to get the identity matrix when we're done, right? So again, it's linearly independent because of the pivot in every column. It spans because of the pivot in every row. It does both because I see the identity matrix when we're done. Okay. So since the reduced row echelon form is the identity, we see that the set is a basis for P3. Is that okay? All right. Okay. Why do we care? What's the big deal about a basis? So we've already alluded to, like we said in Calc 3, or what we've done earlier this semester, if you have that set of vectors, that I, that j, that k, I know that I can express any vector in Calc 3 as something times I plus something times j plus something times k. And if I change those coefficients, I change the vector, right? There's a unique representation. Like there's a unique representation for an ordered pair in R2 or an ordered triple in R3. The idea is that if I have a basis, that means that I can write everything in the vector space as a linear combination, and there's only one way to do it. It gives me a unique representation. That's what this says. Okay. So the reason why this works, it's not too bad to prove this one. Oops. Let's just start with our basis and some vector in V. Why do I know that there is a representation of W as a linear combination? What about being a basis tells me that a linear combination actually exists? It spans, right? That's the whole idea, right? Spanning means that I can write it as a linear combination. So since S spans V, there exist C1, C2 out to Cn, such that C1 V1 plus C2 V2 plus Cn Vn equals W. That's literally what span means, right? We wrote that definition down at the beginning of the class. Does anything about spanning tell me that it's unique? No, it just tells me that one exists, right? So it must be the linear independent part that gives us uniqueness. Okay. So how do we typically prove uniqueness in math? What do we typically do? If I want to show that something is unique, what do we typically do? Start with 2 and show they're the same. That's exactly right. It's typically how we prove that things are unique in math, right? start with 2, show that they actually are identical, right? So let's now suppose that there exist D1, D2 out to Dn, such that D1, V1 out to Dn, Vn equals W. Suppose that we have a second linear combination that gives us W. We used, and I've already mentioned this a minute ago, but we used span to get existence. We're going to use linear independence to give us uniqueness. Now again, from the definition of linear independence, what specific linear or what specific vector do we look at for a linear combination of? For linear independence, what specific vector are you looking at as linear combination of? The 0 vector, right? Looking at these two linear combinations, what can we do to introduce the 0 vector? Subtract them, right? Subtract them from each other. If I subtract, and combining like terms, we'll have a C1 minus D1 times V1 plus C2 minus D2 times V2 all the way out to Cn minus Dn times Vn equals the 0 vector. Right? Subtracting the two, combine like terms essentially. Do we have a linear combination that gives us the 0 vector? Yes. Do we know that the set that we're talking about is linearly independent? Yes. So then what does that tell you about every single constant? They're all 0, right? So since S is linearly independent, we see that C1 minus D1 equals 0, C2 minus D2 equals 0, all the way out to Cn minus Dn equals 0. Or if we just rewrite this, C1 equals D1, C2 equals D2, out to Cn equals Dn. So like Austin said, we started with 2 linear combinations. What did we just show here at the end? Were they really different? No, they're literally the same linear combination, right? And this is very, very common in mathematics to show that something is unique by start with 2, show they're really the same. Right. So hence, the linear combination is unique in this case. All right, questions on that proof at all? Yes. What tells us we have what we need to? Anytime that you're trying to prove uniqueness, this says exactly one way, right? So anytime you're trying to show something is unique, you want to assume that there's 2. Yep. All right. So let's see if we can do these in this next example. The first part is literally like the examples we've already done. First thing it tells you to do is show that this is a basis. How do we do that? Make sure that they're linearly independent in spans. And we do that by doing what? Matrix, right? Make a matrix and row reduce. Fantastic. How do I make my matrix? Where does that 5, 2, -7 go? Yeah, down a column. Good. Next one. Good. Second column. Next one is the third column, right? Now this one literally says show that it is a basis. It doesn't say determine whether it's a basis. So you can probably guess what's going to happen, right? You row reduce it. What should we see? The identity matrix. Fantastic. Good.
Does it have to be both linearly independent and span?
To be a basis, it has to be both. Yes. Yep. To be a basis, it has to be both linearly independent and span, which means that your matrix better be square to start with, all right? If it's not square to start with, you should be able to tell one automatically. For example, if there had been a fourth vector in here, which couldn't it have possibly done? If it had been a fourth vector, which could it not possibly be? Can't be linearly independent. I run out of columns to get for pivots, don't I? If I would have only had two vectors in there instead, then it couldn't span because again I run out of rows to get pivots. Right? I run out of things. All right. So anyway, so this shows that it is a basis, right? Again, pivot in every column. Pivot in every column. That's the linearly independent part, right? Pivot in every row. That's the span part. That part okay? All right. The next part doesn't tell you, we haven't talked about this yet, okay? But the idea, it should make sense to you if you think about what you do with the IJK business, right? So remember that if I write something as x times I plus y times j plus z times k, that's the same thing as x, y, z, thinking of it as a vector, right? These would be the coordinates, correct? In that case? So when something's asking you for coordinates relative to a basis, what they're looking for are these coefficients, those constants that you need. Okay? So what we want to find is what we need to multiply the first vector by. Oops. What we need to multiply the second vector by, and what we need to multiply the third vector by to get the vector that's listed. Oops. I don't know where I got 16 from. Okay. What we're looking for when it says find the coordinates relative to a basis, the coordinates are these constants. Okay? That's what it's asking you for. We know that there's a unique solution to this because it is a basis, right? We don't get multiple solutions, we get exactly one, right? Can you see a system of equations set up to solve? I would have to have 5c1 plus 4c2 minus 3c3 has to equal what? 24. 2c1 minus c2 plus c3 has to equal 13. And the other one also works, right? When I set that up, notice that your first vector is going to go down the first column. Your second vector will go down the second column. Third one will go down the third column. And then we augment to the other one. Right? Again, that's because the 5, the 2, the -7 all have the same, they're all the coefficients of the C1, right? Same thing for the next one for the C2 and so on down the line. Solve this one by row reducing. We already know we're going to get the identity here. If you type that in, what do you get?
6, -3, -2.
Good. Okay. All right. So the way we would write this is my vector. That's my vector in R3. I'm going to put another set of parentheses around it because it doesn't necessarily have to be a vector in R3. It could be any vector. I'm going to put a little subscript of S. So the parentheses here with the subscript of S is telling me I'm coming up with a coordinate vector. It's the coordinate vector of this relative to that basis. That's why there's an extra set of parentheses there. Pardon me. And then the coordinates here will be 6, -3, -2. Now, it's important that we have what's referred to as an ordered basis. This is the coordinates relative to this basis in that order, right? So this tells me I'm taking 6 times the first one, -3 times the second one, -2 times the third one to get the vector that we're talking about. But again, your answers here are going to be what your coordinates are. What questions do you have? All right. So, in general, again, we talk about basis just being a set that's linearly independent and spans, right? But there are some standard ones. We've talked about the standard one for R3 quite a bit when I've alluded to Calc 3 and using the I, J, and K, right? What do you think the standard basis is going to be for R3 then? What vectors do we use? We've already seen it earlier today. What vectors do we use? What vector can generate the x coordinate? 1, 0, 0. Good. What vector can you use to generate the y? 0, 1, 0, and then 0, 0, 1. That's what we refer to the standard basis for R3. We can certainly extend that to any Rn. I need to generate the first coordinate. I need to generate, I should say component. I need to generate the second component. I need to generate the third component all the way down to, I need to generate the last component. Oops, forgot my dots there. How many vectors are in that basis? 10, right? Because I have to generate each component separately, right? Certainly, you can check pretty quickly that this is a basis, because again, form your matrix by putting them down as columns and row reduce. But if I take those specific vectors and make columns, what vector or what matrix do I get? I get the identity matrix, don't I? Automatically. All right. So this is what your standard basis looks like in any Rn, and there will be n of them in there. Okay. It's an important idea we're going to come back to here in a minute. All right, what do you think the standard basis for P2 is going to be? P2 is polynomials of degree 2 or less, and then include your 0 polynomial. If you think about generating a degree 2 polynomial, what do you need to know? If I want to generate just a degree 2 polynomial, what do you think we need to know? The constant and the coefficient of the x and the x squared, right? I'm going to need 3 of them, right? So what do you think, what 3 specific polynomials do you think we would use to generate those, if we want to call it a standard one? What polynomial do you think we would use to generate the constant term? The 1, right? Use that specific one, right? Because I can take it times any constant, right? What polynomial do you think we would use to generate specifically the x term? X, good. And what polynomial do you think you would use to generate the x squared term? X squared, good. That's what we would use for our standard one. And think about why. Because again, if I have any polynomial, I can write it like that, can't I? Right? And then I'm looking at my A, my B, my C. Okay. So then if you wanted to extend that to Pn, what do you think you would use?
X squared and x to the n.
Good. All right. How many vectors are in that set? N plus 1, right? Because I got to generate all the powers of x and a constant, right? So there's n plus 1 of them. So notice your P2 has 3 vectors, your Pn has n plus 1 vectors. Again, we're going to come back to that idea here in a minute. That okay? All right. How about M23? What does M23 mean again? Yeah, what size matrices? 2 by 3, right? So how many entries do we need to generate? 6. How many things do you think are going to be in your basis then? Yeah. I mean, how many elements do you think we're going to put in our basis? If I need to generate 6 entries, how many things do you think we're going to need? Probably 6, right? Think about it up here, right? How many components did we need to generate in Rn? N of them, right? So I have n things in my basis. How many things do you have to generate when you're in a polynomial of degree n? I got n plus 1 things to generate, don't I? Here I have 6 entries. I better have 6 things to generate them. If it's going to be standard, what 6 matrices do you think you're going to use? Well, I want a specific matrix, right? I don't want to use letters. I want to use specific things with specific numbers. If I want to generate the first and the upper left entry, the 1-1 entry, what do you think we might want to use? The 1 in rest zeros, good. If I want to generate the 1-2 entry,
0, 1, 0.
in the rest zeros, right? Yep. And then just keep going all the way across, just like what we did in Rn, right? Same concept. Same concept. And get all 6. A little harder to write it out for general M by N matrices, right? A little harder to write it out. But you could do it as general entries if you wanted to. I'm not going to try to write it out anyway. Right? How many matrices do you think we're going to need if we have general M by N matrices? M times N. Good. We need M times N matrices, each with all zeros except 1 entry that is a 1. Just like what we did above. All right. So I've already mentioned this several times that we've gone through and said looking at how many elements are in a basis, right? So R3, there was 3 elements in a basis. The Rn, there was n elements in a basis, and so on down the line. That's what's going to give us our idea of being what dimension of a vector space is. Before we get there, your book has a couple of definitions of what we mean by finite dimensional versus infinite dimensional vector spaces. A vector space is called finite dimensional if it has a finite basis. What I mean by that, of course, is that there is a finite set of vectors that can generate everything in the vector space. Okay. I'll just write that down. In other words, every vector in V can be written in terms of a finite number of vectors in V. There's a finite set that generates everything. So infinite dimensional must mean it's an infinite set that does that, right? So all right. So notice that the examples that we had that we listed above for your Rn, your Pn, your M by M of Mn, M by N matrices. Say the word that I'm trying to say. All of those are finite dimensional because all the bases are finite sets. Okay? I can write everything in those vector spaces as a linear combination of a finite set of things. Can you think of a vector space that might be infinite dimensional, where you can't just find a finite set to generate everything? Can you think of a space that might be infinite dimensional? Say that again. That would be an example of an infinite vector. You're right. R infinity, if you have infinitely many components, you could actually do that. Absolutely. That would be an example of an infinite dimensional vector space. You can think of that as the set of all sequences where each term of your sequence is a real number. So you've done sequences. If you've had Calc 2 or Calc 3, you've done sequences before. You can do the set of all sequences as an example of what would be an R infinity type of thing. Yeah. Any other thoughts of things that we've talked about this semester? What are your, if you have differential equations or are in differential equations, what do your answers usually turn out to be? What kind of objects are your answers? Not a trick question. What kind of things are usually answers to differential equations? It's that dirty 8-letter F word. Functions. There you go. Yeah, it's a function, right? Your answers are usually functions. Function spaces are typically infinite dimensional. So we've talked about your your continuous functions on an interval or differentiable functions on an interval. Those are examples of infinite dimensional vector spaces. Think why. What kind of functions are continuous? Polynomials, rational functions on their domain, right? Trig functions on their domain, exponentials, logs on their domain, right? Get lots of different examples, correct? And I can't generate a trig function from an exponential, for example. Okay. So those are examples of infinite dimensional vector spaces. So we've already talked about those kind of things. All right. So we want to get to the idea of what we mean by dimension. Dimension of a vector space is going to be the number of elements in a basis. So what this theorem talks about is the fact that if you have bases, two different bases, they may not be the same set, but they have to have the same size. Okay? If we think about it in terms of the row reducing idea again, we can see what the idea of this proof is. I'm going to go through one of them and leave the other one for an exercise, if you will. I do have a typo here. These should be W's here, not V's. It should be a W1, a W2, and a WM. All right. So let's think about why this has to be true. If I have more vectors in my set T than I have in this basis, why does it have to be linearly dependent? Now, let's think about it in terms of the row reducing argument that we talked about before, right? If this is a basis, what kind of a matrix do I get if I take those vectors and put them in as columns of the matrix? What size does it have to be? It has to be square, right? If it's going to be a basis, right? If M is bigger than N, am I going to have a square matrix? No. Which is going to be bigger, the number of columns or the number of rows? If M is bigger than N, number of columns, right? So if I row reduce, can you get a pivot in every column? No. Right? So it can't be linearly independent. So if you think about it from a row reducing standpoint, that should make sense, right? I get more columns than I have rows, so it can't be linearly independent. It has to be linearly dependent. Now, I don't necessarily know that these vectors are easily put into columns of a matrix. We need to prove it more generally. The way the proof goes is the following. Since our V1 out to Vn is a basis, then we can write each of our W sub I as a linear combination. of the V's. So what we mean by that is that I could do a C1 1V1 plus a C2 1V2 plus a CN1 VN equals W1. Do the same thing. Oops, let's do that backwards. So 1, 2. Do the same thing for W2. All the way down to WM. This is because the basis has to span V. Our W's are in V. The V's span V. So I can write each of the W's as a linear combination of the V's. What does it look like I'm trying to set up, by the way, the way I wrote this? Yeah, I'm going to try to make a matrix out of this, right? Set up a system of equations, right? I don't know what the vectors look like in general, but I do know that this class is called linear algebra. I probably want to find a system of linear equations. Okay? That's the idea. All right, what am I trying to show? I want to show that the set of W's is linearly dependent. Linear independence or linear dependence talks about a linear combination that gives me the zero vector, right? To start with? Agreed? Okay. So, pardon me. Let's consider a linear combination. I'll call it K1 W1 plus K2 W2 plus Kn Wn. Let's start with a linear combination that gives me the zero vector. If it's going to be linearly dependent, what do I need to argue? What needs to be true? Do I just get zeros for the k's, or should we have infinitely many solutions? If it's going to be linearly dependent, it better be infinitely many solutions, right? So we're going to set up a system of equations that we know has infinitely many solutions. Okay. All right. So just to save some time, we have these linear combinations here, right? We agree? We have those linear combinations there. Okay. We can substitute those in for each of the W's and rearrange, right? So what's going to be multiplied by the V1? I'll have a K1 times C11. I'll have a K2 times C12, all the way to a Kn times C1m, right? For my V1s. So if we rearrange and substitute and rearrange, I should say, substituting and rearranging, we have what? We've got C11, K1, C12, K2, out to C1m, Kn. Oh, it's Km, not an N. That's my problem. Because there's MWs times V1 plus same thing for the V2. And then all the way down to the N's. Equals the zero vector. I started with a linear combination of the W's that gives me the zero vector, right? Now what do I have a linear combination of? What vectors are we, now do we have a linear combination of? In the V's, right? I got a linear combination of the V's, don't I? What are we assuming about the set of V's? It's a basis. In particular, it's linearly independent. So what would have to be true about all the constants then? They're equal to 0, right? So since our V1, V2 out to Vn is linearly independent, we have, I'm going to need a little bit more room. What did I tell you to start with? I wanted to create a system of equations, right? So that first coefficient has to be 0. The second coefficient, has to be 0. All the way down to the last coefficient has to be 0. Right? It's linearly independent, so the constants all have to be 0. Okay? Right? How many equations are there? How many coefficients were there for the V's? How many equations do we have? N. How many variables are we trying to solve for? M, right? The K's are the variables that we're trying to solve for, right? So we have N equations, M unknowns. Oops. What kind of system do we have? When we have zeros all on the right-hand side, what kind of system do we have? Homogeneous, right? We also know that which is bigger, M or N? The M is bigger in this case, right? Right? I have more unknowns than equations for a homogeneous system. What does that tell you? If I have more unknowns than equations, how many solutions do you get? Infinitely many, right? There's infinitely many solutions for the K's. Going back over here, does that mean that this linear, can I write the 0 vector in only one way as a linear combination? No. Okay. So that's what tells us that set T is linearly dependent in that case. All right. So I know it was a lot and it was quick. The reason why it was quick is I don't want you to reproduce this on a test. I want to tell you why it was true. Here's the conclusion. If you have too many vectors, and by too many I mean I know what a basis is, and I've got more vectors in another set, it cannot possibly be linearly independent. Okay? If you have too many, can't be linearly independent. Okay? The next part says if you have too few, then it can't span. Okay? The proof of the second part is much like the proof of the first part. You just have to rearrange it a little bit. It's not too big of a deal. Okay. So what does this tell us? The crux of this is that every basis for a vector space has the same size. That's what it tells us at the end, is that every basis has the same size, and so that lets us give us the definition of the dimension. The dimension of a finite dimensional vector space is the number of elements in a basis. Okay? So let's do this examples real quick and then we'll finish this up on Wednesday. There is one special case. The zero vector space, the vector space that contains only the zero vector, has dimension 0 and it has an empty basis. That's a special case. Just we don't deal with that one very often. It's the only vector space that has a finite number of vectors in it. For our purposes. All right, how about the other ones? Well, how many elements were in the standard basis for Rn? N. So every single basis has n vectors in it. So what's the dimension going to be? N. Good. What size did our Pn standard basis have? N plus 1. That means every basis has n plus 1 vectors in it. So the dimension is going to be n plus 1. So for mn, the m sub mn, how many vectors did we have there? M times n. Good. Now let's look at this last one just real fast. The solution space. Remember how we did solution spaces? What did we look for first? How did we write our solutions? What did we look for first? The free variables, right? How many free variables do you see here? 3 of them, right? And then I can write everything else in terms of those 3. Remember when we wrote those solutions out as something times a vector plus something else, right? How many vectors do you think we're needing our basis here? I'll need 1 for that one. That could be anything. I need 1 for that one and 1 for that one. Okay? So the dimension here will be 3, which is the same as the number of free variables. All right. We'll talk about that one again on Wednesday. Then we'll finish this section up. I did notice when I went and looked at WebAssign, a number of you had not done the homework that was due right before break. I went ahead and just granted, if you didn't do it, I granted an extension, so you'll have till tomorrow to get it done in WebAssign. Okay. All right. All right. Have a good one. By the way, there's already a review for the exam posted on Moodle with answers, so you can check that out. Yep, this section's on the exam too. Yep. All right. Have a good one. We'll see you on Wednesday, if not before. Yeah.
How did you layer when you're combining this with this? Why didn't you care about the W's? Like, or it's just
I took this in my W1, I substituted. I took this linear combination and substituted it for W1.